Okay, so we are in Statistical Rethinking, second edition. We're in chapter 9 and we're just starting the hard questions. So we're on question 9H1. Okay, so we are supposed to run this model right here with the rethinking package, and then compare samples for A, which is a normal distribution, and B, which is a Cauchy distribution, I believe is how you say it, or Cauchy. Well, we're going to look at the trace plots and kind of discover some things about trace plots as well as the Cauchy distribution. I should say before you do any of this, you will need to make sure that you have installed and loaded Stan and the rethinking package, and you can do all of that with these first few code blocks at the top of the Colab sheet. This second block, I believe you just need to run it one time. I could be wrong, but if you've done this more than once, it will throw an error and you can just proceed and it installs just fine. So anyway, let's get back down here. Where are we? Okay. So we have our model and we're going to run it. One of the things that it asks is, what is this model accomplishing? I'm not really sure what that means, but notice that A and B, these are just prior distributions. We're just simulating from two different distributions here. So there's no linear model or anything like that. So I think that's maybe the answer to what is this accomplishing. It's just demonstrating the distributions of A and B. And in another context, we would call these the prior distributions if we were going to try to update them. Okay, so the question displays using just one chain, but I'm going to use two just because it makes the trace plots maybe a little bit more interesting. But anyway, so you run this, and I've already ran it, but again, it takes a few seconds, and so I don't want to record that. So we have all of that, and so now I'm going to get the pricey and the trace plot. So here's the summary, and so we see that they've sampled probably pretty well, and we can tell because they have pretty low R-hat values approaching 1, and a reasonable number of effective samples. But now this is the these are the trace plots, and I'm actually going to open this in a different thing here and just kind of zoom in. And so the normal distribution, the one on the left, A, looks about what we should expect it to look like. Okay, right? It's kind of that fuzzy caterpillar type look, right? It looks like there's good mixing, and the two chains look like they're reasonably similar. But then we come over here to the to B, which was the Cauchy distribution, and this looks maybe pathological, right? We have these. It doesn't really look like a fuzzy caterpillar anymore. It looks like a smushed bug with many legs or something like that. Okay, so so that's interesting. But let's examine that a little bit further. Well, the first thing I want to notice here is that notice that the y-axes are very different. Remember, the y-axes are the parameter values that are being sampled by our Markov chain, and our normal distribution goes from like 0 to 3, or -3 to 3 roughly. But the Cauchy goes much larger than that, right? It's the y-axes are around magnitude of 100, and if we ran this for longer, they would even get bigger. Okay, and so if I were to zoom in, and I can only do this so well on here, but if I were to zoom in, 3 would be pretty low, and just this central part kind of probably does look like a fuzzy caterpillar. Okay, and that would make sense because we saw with the pricey output that it seems that even though we have this kind of weird looking trace plot, that the sampling was good, and it probably was good if we limit, well, this is a weird way to say it, but if we limit our view to just a little bit on either side of 0 rather than going all the way to 100. So what is happening with these big, large excursions in possible parameter values? And so to understand that, we need to understand a little bit about the Cauchy distribution. So so you can look up the formula, but I think for here it doesn't really do us much good just to see the formula. It's, it's hard to get an intuition for the formula. So one way that we can think about what the Cauchy distribution is doing is illustrated here. So imagine that we have this cannon and it's shooting things, pellets, against a wall here. Okay, and so hopefully maybe it's not cannonballs or something, but something that won't destroy the wall. And this cannon is rotating on its horizontal axis, back and forth and back and forth. And wherever a cannonball hits, we're going to call that a data point, roughly. Okay, and so well, actually not where it hits, but the distance from center is our data point, right? So this distance from the center to here is our data point. Okay, well, you can imagine this thing going back and forth and back and forth, and every once in a while, it's gonna shoot at a trajectory that sends its pellet or whatever way, 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 way down the wall to where X is going to be just arbitrarily large. Okay, and so those arbitrarily large shots or whatever, that is corresponding to these large spikes in the trace plot. Okay, so one of the consequences of this is that the Cauchy distribution, it's bell-shaped and symmetrical like the normal distribution, but it is much broader. Okay, and so I've generated a normal distribution here in solid black line, and then a dotted red line. Let me nope. And then a dotted red line for the Cauchy distribution. And notice how much broader the Cauchy distribution is. And so especially as you go out towards the tails, it kind of gets it's a little bit difficult to really appreciate this. But as you go out towards the tails, the probability of a very large value in a normal distribution becomes basically zero. But if we were to, if I were to zoom in here, which I'm not doing, but you would see that the red, for extreme values, the red is always the probability of an extreme value for the Cauchy distribution is always greater than for the normal distribution. And so when you get way, way, way out into the tails, there's still a non-negligible amount of probability that a arbitrarily large value from a Cauchy distribution will be drawn. Okay? So one of the consequences is of how the Cauchy distribution is being generated is it's broader. It has very fat tails, is what you might call it. Okay, and then another consequence is illustrated here. Is illustrated here. This is something I found on Wikipedia, and it's by a man named Jacopo Bertolli. So sorry about the pronunciation, but we have a normal distribution and a Cauchy distribution. And so notice that the normal distribution, as we're drawing samples, right, as we're drawing samples from the normal distribution, the mean, mu hat, and sigma hat, or standard deviation, they converge to some value here, right? So these are both, I think these are both 0, 1 or maybe 0,10 distributions, but it doesn't matter. But the important thing is that the normal distribution converges over time, many samples, to a particular value for each of these parameters. However, the Cauchy distribution, because it's getting extreme values semi-frequently, whenever it gets one of these extreme values, it jumps one way or another, right? And so it doesn't really settle down to a particular mean, and it doesn't settle down to a particular sigma value either, right? Again, because these large values are sending both the mean and the standard deviation into the stratosphere. So anyway, I guess that's what we will stop on here.